All right, here we go. So today's lesson, we're going to start learning about waves, and then the intent of this video is basically just to help you with the basics of waves. So we'll be learning about different types of waves and the properties of those waves. Here we go. First of all, these two definitions are stolen from the author of your book, from Hewitt. He describes a vibration as a wiggle in time and a wave as a wiggle in space and time. So all he's getting at there is this, that a vibration looks like this. You've got a particle or an object or something at some point, and if it's vibrating, it just means that it's going back and forth, back and forth, back and forth like this. And so all of the energy is kind of localized in one spot. Now, a wave is the same thing. You've got this particle that's going to vibrate back and forth, but as it does it, it travels through space, giving you this kind of thing. Okay? So that's the main difference between a vibration and a wave, is that the wave transfers energy from one location to another. In this case, the energy is traveling this way, as the particle, in this case, the particle is vibrating up and down. But so the point is, you've got these vibrating particles, and because of those vibrating particles, it carries energy through space. All right, so that's the main difference between a wave and a vibration. Okay. So we're going to talk about two different types of waves. All right. What we're going to focus most of our energy on is this first type, what's called a mechanical wave. All right. A mechanical wave is, when you think of a wave, probably what you're thinking of. If you picture like water waves or a wave at a stadium or like a wave on a slinky or a string or something, that's a mechanical wave. Because what they're doing is they're transferring kinetic energy. The particles are vibrating, causes a chain reaction, causing particles farther away to vibrate. What is important about mechanical waves is they have to have a medium to travel through. Like it says here, medium is basically a fancy term for the substance that vibrates to carry the kinetic energy. In the case of a water wave, the medium is the water. If you do the wave at a stadium, you know, where everybody stands up and sits down, that thing, there the medium is people. If there's no people in the stadium, you're not going to have a wave. Okay? And then the second type of wave is what's called an electromagnetic wave, and this is actually going to be your next test, like your next chapter. Electromagnetic waves, like light and X-rays and UV rays and all that, are a transfer of electromagnetic energy instead of kinetic energy, and they're caused by vibrating electric charges. Electromagnetic waves are unique because they don't have to have a medium to travel through. And so electromagnetic waves can travel through a vacuum, which is, for example, why we're able to see the sun, right? The sun transfers its light to the Earth, that's the Earth, through the vacuum of outer space. Okay? And I guess I should probably comment, every once in a while somebody asks this. The word vacuum just means empty space. It's a space that is completely free of anything. No air, no water, no dust, no motor cars, nothing. All right? Cool. So there you go. There's the two types of waves. Again, from this point forward, this chapter, we're really going to be focusing on mechanical waves. All right? So, within that, there are two types of waves. Within mechanical waves, rather, there's two types. There are transverse and longitudinal waves. Okay? These definitions should hopefully look relatively familiar. A transverse wave is a wave in which the direction the particles vibrate is perpendicular to the direction the wave's energy is traveling. So you might have a particle, you might have a particle vibrating up and down, but the energy would get transferred this way. Okay? Now, with a longitudinal wave, in order for the energy to travel this way, again, like the other one, what you'd have to have is you'd have to have particles vibrating back and forth this way. Okay? So, transverse, the particles vibrate perpendicular to the direction the energy goes. In longitudinal, they're parallel. Okay? So, this is really tough to draw, so probably the best thing for us to do is to see it. So, let's do that. All right, so, let's scroll down here. All right, so here is an example of a transverse wave. Okay, what we've got is, if you look at any one of these particles, I'm going to see if I can pinpoint a particle. So that particle right there is vibrating down and up, down and up, down and up, down and up. And as that's happening, you can see that if you watch any one of the tops of these waves, the waves are traveling this way. Okay? So that's a transverse wave because the motion is perpendicular to the direction the energy is traveling. Okay? So now let's take a look at longitudinal waves. Oh, I always do that. Let's take a look at longitudinal waves. So here's our longitudinal waves. The longitudinal waves, if you watch the particles here, the particles now are going back and forth, back and forth, back and forth. And the wave's energy is traveling this way. So in this case, they are parallel. Okay? So that's a longitudinal and transverse wave. Okay? Now, you need to know the parts of these two types of waves. All right? So I believe that the next page has those. All right? So here's a drawing of our transverse wave. All right? The transverse wave looks like this. More often than not, if you were to draw it, it would look like this. Okay? And so the idea is you've got sort of high points and low points. Okay? The high points are called crests, and the low points are called troughs. Okay? And then the height of a crest, this distance here, or the depth of a trough is called amplitude. All right, I'll give you a definition of that in a minute, like written out. But that's the height of a crest or the depth of a trough. Okay. Please keep in mind that if you watch one of these particles, like this represents a particle, that particle is going to go down and up, down and up. The amplitude is just half of the distance that it goes. Okay. So that is the deal with transverse waves. So now let's talk about longitudinal waves. All right, longitudinal waves don't have crests and troughs. They have what are called compressions and rarefactions. Unfortunately, I did a screenshot of this, and it really didn't capture very well. But if you go back to the video that we, the graphic that I showed from this, there are points where the particles are kind of very close together. Okay, those points are called compressions. In fact, a longitudinal wave is often called a compression wave. Okay, so those are sort of analogous to the crest of a transverse wave. All right, there's also these other spaces where the particles are farther apart. All right, and those are called, and this is a weird word, but the spaces where the particles are farther apart are called a rarefaction. Rarefaction. Okay? And those are caused just by the particles vibrating back and forth. All right? So amplitude you really can't draw on this because what's going to happen is if you pick a particle, so this particle, for example, is going to go back and forth, back and forth, back and forth. So the amplitude would be just half of that distance. Okay? So there you go. Those are the two different types of waves. All right, now let's talk about some other things that we can measure. First of all, I'm going to do this out of order. Amplitude, we just finished talking about. Units that amplitude would be measured in is meters, and it's the maximum displacement of a particle's vibration. It's half of the distance the particle goes back and forth. I just showed you that. People often say, and I even said this, that amplitude is the height of a crest or the depth of a trough, which is fine if it's transverse wave, but it doesn't help us for longitudinal waves. So I really like this definition better, the maximum displacement of a particle's vibration. Conceptually, understanding it this way, half the distance makes sense too. All right. The amplitude is determined by the size of the particle's vibrations. The more the particles vibrate, the more the amplitude is. If all of the things are constant, a larger amplitude just means that the wave is carrying more energy, which makes sense. If you're, standing at the beach and you get hit by a bigger wave has a bigger chance of knocking you down because it has more energy, right? Okay. And then the next thing that you need to know about is what's called wavelength. Wavelength is defined as the distance between two successive crests or troughs or identical points on a wave. All right. If it's a longitudinal wave, then it would be the distance between two successive compressions or rarefactions. So jumping back to things, let me kind of clear this up a little bit. All right, so our wavelength then would be, draw it in green here, the distance between two crests, the distance between two troughs, or the distance between any two identical points. Okay, so that's wavelength. The symbol that I'm using here is the Greek letter lambda, and it stands for wavelength. Okay? For a longitudinal wave, the wavelength is just the distance between two compressions, or between two rarefactions. Okay? Oh, no, sorry. Yes, I was done with that slide. All right, cool. All right, the next thing we need to understand is period and frequency. I'm going to give you a few different definitions here. Take a second and write them down. The big thing that I want to call attention to, apart from the definitions, is this, that the period is determined by how quickly the wave source is vibrating. Okay, the faster it's vibrating, the smaller the period is going to be, because it takes less time to go back and forth once. All right, and then frequency, same thing. The faster it's vibrating, the bigger the frequency. Okay, so write those down. And then down here at the bottom, remember we learned this when we did circular motion, period and frequency are reciprocals, right? Period is the seconds per vibration, or the number of seconds per wave, and frequency is the other way around, vibrations per second or waves per second, which gives us these two equations here. Okay, in other words, if you know your period, you can find your frequency, and vice versa. All right, so let's take a look at this so that we can get kind of a visual. Oh my gosh, why are there a bazillion windows open? All right, so there we go. So here, I'm going to look at transverse waves here just because they're easier to understand. So here, the medium that this is traveling on is sort of a string of beads. And you can see that over here on this side of the screen, we've got this little thing that's going, there's no way I'm going to be able to do it, but up and down really quickly, right? Okay. How quickly that goes up and down determines both the period and the frequency. Okay, so let me run through the definitions of frequency and period. So period would represent the amount of time that it takes for one of these three things to happen. It's the amount of time it takes for the vibrating source to go from here to here. Okay, so if you were to use a stopwatch and time how long that took, that would be the period. Or you could do it for any individual particle on the wave. You could time how long it takes for, say, this particle right here. Let me put a dot there. This particle right here, we could time how long that particle takes to go from here to here. And that would also give us the period. Okay? Okay, so that would also be the period, the time that takes. Or the final option is time how long it takes for the wave to travel one wavelength. So right now my wave is, there's a crest right here, right? So if I measure how long it takes for this crest to go one wavelength, that will also be a period. Okay, so if we unpause it, we can see what will happen is the arm will go up and back down and back up again to its starting point in the same amount of time it takes for the wave to get from here to here. All right, so I'm going to attempt, I don't know if this will work or not, I'm going to attempt to unpause it and then repause it at the exact right moment. So here we go, boom. Oop. No, fail. All right, but anyway, what would have happened there is in the time that it took for the arm to go up and down, the wave would have traveled that far, one wavelength. Okay, so there you go, that's period. Frequency is the opposite. Instead of measuring the time per wave, it measures the waves per unit time. So if you measured in 1 second, what would happen is this arm would go up and down. Arm would go up and down some number of times in 1 second. This particle over here would go up and down that same number of times, and this wave would travel the same number of wavelengths. So in other words, here the frequency is set at 50. Unfortunately, the units aren't calibrated. But what that's saying is, if this particle goes up and down 50 times in a second, then this particle goes up and down 50 times in a second, and this point here would travel 50 wavelengths forward. Okay? So that is frequency and period. So let me clear this board up a little bit. All right, I'm going to unpause it and show you how changing things affects the look of the wave, I guess. All right, so first thing I'm going to do is show you when you change the amplitude all that does is change sort of how much the particles vibrate, but it doesn't affect anything else. All right. So right now the wave is traveling this way at a certain speed, right? And so when I change the amplitude, it doesn't change how quickly the wave travels, how quickly the energy travels. So here's a really big amplitude. Oops. Here's a really big amplitude. Or here's a very small amplitude. But whether the amplitude is big or small, the energy is still carried this way at the same velocity. Okay? So let's set this back to about 50. There we go. All right. Now, the other thing we can change is the frequency. The frequency is a measure of how quickly the particles vibrate. So I can make the particles vibrate faster, or I can make them vibrate slower. Okay? Now, all that's changing there is how quickly the arm is going up and down. Okay? And as that changes, your wavelength changes too. All right? It turns out, though, that what does not change is the velocity of the wave, which is what the next slide is about. So I'm going to come back to this visual in a minute. But before I do, I want to show you a couple other things. So wave speed or wave velocity is the rate at which the wave's energy moves. It's how fast the wave carries its energy forward. All right. This, what is written in giant letters, is colossally important. Please write this down and put giant stars and arrows and stuff pointing at it. The wave speed, how fast the wave travels from point A to point B, how quickly it carries the energy, is determined only by the medium it travels through. The only thing the wave speed depends on is the medium it travels through. And as an example, here's this. The rate at which sound travels depends on the medium it travels through. Okay? So for example, 25 degrees Celsius is about room temperature. Any sound wave in the entire universe, if it is in regular air at room temperature, sorry, it'll have a velocity of about 346 meters a second. So whether I talk very quiet or very loud or in a high-pitched, I was trying to do, in a high-pitched voice or a low-pitched voice, all of those sounds that I just created are coming out of your speakers or out of your headphones, and those sound waves are all traveling at the same speed. Okay? The only difference is the frequency would be the pitch, right? High frequency, low frequency, or the volume actually translates to the amplitude. All right. So what that means for us then is this. Okay, so is this recording again? Yes, it is. Okay, cool. Here are the equations that we use to relate these. All right. All right, so it turns out you can find the velocity of a wave. You can find the velocity of a wave by taking the frequency that the particles are vibrating at and multiplying that by the wavelength. All right. In terms of calculations, this equation is probably the easy one to use, so I would write that down. In terms of understanding it conceptually, I actually like this one better. Okay, because it turns out the velocity, you don't have any control over it. The velocity is going to be determined by the medium that the wave is traveling through, right? If you're talking, you don't have control over the medium. You're talking in air, right? And you're going to divide that by the frequency. The frequency is determined by how quickly the particles are vibrating. Again, you don't really have too much control over that unless you're vibrating to create the waves yourself, okay? I guess that's not true, but anyway. And so then the wavelength then depends on that, depends on those two things. The wavelength depends on the velocity and the frequency. Please don't make the mistake of thinking that as the frequency increases, the velocity increases. A lot of times, especially coming from chemistry, people look at this equation and they think, oh, bigger frequency, that means bigger velocity. But that actually turns out not to be the case. Okay, this is super important, so make sure you hear this. Bigger frequency does not mean bigger velocity. Okay? As the frequency increases, the wavelength decreases because the velocity doesn't change unless the medium changes. Okay? And we saw that in our graphic back here. Okay, look. Here we've got a pretty small frequency, right? And right now our wavelength is, if we pause this, our wavelength is Let me unpause it. So right now, we've got a small frequency and a big wavelength, right? Cool. So now what I'm going to do is I'm going to unpause it, and I'm going to increase the frequency. So here, let's increase our frequency, and then pause it again. And now we've got a much smaller wavelength, right? But a bigger frequency. So bigger frequency, smaller wavelength, but you get the same velocity. Okay? So the only way to change the wavelength is by changing either the frequency or the velocity. All right? Ultimately, the wavelength depends on the velocity and the frequency. Okay? Cool. I think we are almost done. I'm a little over 20 minutes. I apologize. Have I missed anything? We talked about wave speed. We talked about velocity. I gave you the equations. Don't make that mistake. Oh, example. All right, so we're going to do an example, and then we're done. So, example. Frank makes a water wave in the bathtub by tapping the water twice per second. The resulting waves are 0.25 meters apart. So let's write down what we know. Twice per second. That's telling you that the frequency of vibrations is 2 vibrations per second. It's the same as 2 hertz, right? That is our frequency. That's how frequently he's tapping the water, twice per second. And then the waves that he produces are 2 meters apart. That's the wavelength. So for part A, to find our velocity, it's frequency times wavelength. We've got 2 waves per second. The wavelength is 0.25 meters per wave. Waves cancel out, and you get 0.5 meters per second. Okay, so that's part A. Part B says, how far apart would the waves be if you tapped the water 5 times per second? I like this question because it really forces you to think about something, which is this. What did we do? We changed the frequency to be 5 hertz, right? And we're trying to find how far apart the waves are. We're trying to find the wavelength. Well, what's the velocity? Well, remember, the medium hasn't changed at all, so that means our velocity is still the same. Our velocity is still going to be 0.5 meters a second. So based on that, we can find the wavelength. Okay, so now what we can do is find our wavelength, right? Remember, wavelength is velocity over frequency, right? So we've got a velocity of 0.5 meters a second. Our frequency is now 5 hertz. So divide that, and you're going to get, what, 0.1? Yeah, 0.1 meters. So now the waves are much closer together because there's more of them per second. Okay, so there you go, waves. Sorry I went a little over. Hopefully that was easy, though. It should have been a lot of review. Have a good day.